Now we are going to look at rates of change and how we can use rates of change to solve practical problems, so real world type problems. So questions like this usually come with stories, blocks of text that we have to read and interpret, and sometimes they'll have diagrams going with them as well. So how are we going to use what we know about rates of change, or the derivative, to help us solve more real world type problems? So the rate of change we have been focused on is dy dx. How does y change over a particular change in x? So rise over run. If we run across by a particular amount on our x-axis, how much do we rise or fall on our y? That's been our rate of change, and dy dx is just the instantaneous rate of change. How much are we changing at a particular point? But we can use this idea of how one thing changes as another thing changes, how y changes as x changes, for physical situations too. And the most intuitive one of those is probably speed. So what does speed mean? It means over a particular amount of time, how far do I travel? So if I traveled 100 kilometers in an hour, my speed would be 100 kilometers per hour. So the speed gives me how does my distance change as time changes. So the way that we can write this using our derivatives is using some letters that we might not expect. V is the letter we use for speed, because what we're actually using is speed in a particular direction, which is called velocity. So it's V for velocity, but we can think of it as speed. And we're looking at the rate of change of distance over time. S is the letter that is used for distance, because just like speed, this is actually distance in a particular direction, which is called displacement, which doesn't start with S, but we use S for our distance in a particular direction. So we have V for our speed, and it is going to be the rate of change of our distance with respect to time. So we have dy dx is our rate of change of y as x changes, and our speed is going to be the rate of change of our distance as time changes. Now, building off of that, we also have the idea of acceleration. So what does acceleration mean? It means how quickly do I change my speed? If I accelerate quickly, that means that I'm going to change my speed very quickly. So how my speed is changing, or the rate of change of my speed with respect to time, is going to be my acceleration. Now, acceleration, sensibly enough, is called a, and we have, that's going to be the rate of change of speed, which we use v for our speed, all over time. And if we think about our derivatives, that means this is the derivative of our distance. So the acceleration is also the second derivative of our distance. So if they give us a formula for the distance in our questions, we could get the derivative of it twice. The first time we get the speed, and the second time we get the acceleration. We can also get the rate of change of other stuff. So if we think about the area of a circle, how does the area of a circle change as we change the radius length of the circle? So if we changed the length of the radius, how would the area of that circle change? And we would call that mathematically dA dr. So as the radius is changed, as we change our radius, how does that affect the area? And we call that dA dr. So if we just go back to our normal equations, and we have y is equal to minus 5x squared plus 20. If we wanted to get dy dx of that, we'd just use our power rule. We'd multiply by the power and subtract 1 from the power for anything involving x, and our constants, our stuff not involving x, would go to 0. So we'd end up with dy dx would just be minus 10x to the power of 1. So that's how we take our derivative if we had y and we were getting dy dx. Let's go to a story now and see if we can learn, or if we can figure out our rates of change for this situation. So a ball is dropped from a window 20 meters up. So the window is 20 meters up, the ball gets dropped out of the window. its distance from the ground is given as s. S is our letter for distance. Is minus 5 t squared plus 20. I've deliberately given exactly the same equation as I did for the y and the x formula here. It's just that s is our distance above the ground and t is our time in seconds. So what is the speed of the ball? Well, the speed of the ball is going to be the rate of change of our distance. So this is the distance above the ground. So the speed is going to be how that distance is changing in time. So that means that we're looking for part one, what we're looking for is ds dt. So how do we do that? Well, exactly the same way as we did this here. So we would have s, I should say, is equal to minus 5t squared plus 20. So ds dt, we multiply by the power. Now anything with t in it is what we are differentiating. So multiply by the power, subtract 1 away from the power. Derivative of a constant is just 0. So we end up with minus 10t to the 1. Exactly the same way and with exactly the same result as we did when we had dy dx. So if we're differentiating by t, that's the thing that we're taking, the variable we're differentiating, then we treat it exactly like we treated our x's. Nothing changes. So that's the speed of our ball as time goes on. So we could find the speed then at any time. We just sub in the time we were interested in, and it would tell us the speed of the ball as it's falling. So part 2 asks us, what's the initial speed? Now, one of the difficulties of these questions is that there's lots of, or can be lots of English involved. So what does initial mean? Well, initial means at the start. If we initialize something, it means we're starting something. So at the start, our time would be 0. So if we see this word initial, or if they say what was the starting speed, if they tell us the story of this and they tell us in English that time is 0, we have to be able to recognize and write down that time is 0. So really what we're looking for is, what is ds dt, what is the speed, which can also be called v. So we have v at time 0. This is in function notation, so just like we'd have f of x, we have v of t, and this time t is 0, or we could have ds dt at t is 0. Two different ways of writing the same thing. In any case, we know what ds dt is, we know what the speed formula is, and just from the story of the question, we're told that the ball is dropped. So if we're holding it in our hand at the very beginning, that means when we drop the ball, it starts from a speed of 0. It's going to get faster as it falls down towards the ground, but we actually just drop the ball. That means that it starts off in our hand stationary. So we're expecting that the speed at the start should be 0. So when we sub that into our formula here, is that what we get? We have minus 10 times 0, which is indeed 0 meters per second. I didn't actually say that this was in meters, and I should have in the exam, they probably would, but I did say t is in seconds, so we have meters per second there. So initially the speed is 0. The ball's not moving until I let go of it and it falls down out of the window. So part 3 says the speed when the ball hits the ground. So what is the speed when it hits the ground? Well, this formula gives us the distance above the ground. So when we hit the ground, what's the distance above the ground? Well, it's going to be 0. The ground is a height of 0 above the ground. So s, the height above the ground, is going to be equal to 0. So we want to know the speed, ds dt, when s is 0. So to do that, we need to know when that happens. So when does this ball hit the ground? When is s 0? Well, t is our when variable, it's our time. So I want to know when s is equal to 0. So s is minus 5t squared plus 20. And I want to know what time that hits the ground at. When is s going to be 0? So this is just a quadratic that I can solve, but in this case, the easiest way to solve it would be just to isolate t and take the square root. So I'm going to do that. I'm going to get t by itself, or the t involved stuff by itself. T squared is equal to minus 20. I want t involved stuff by itself, so I'm going to divide both sides by minus 5. So t ends up being equal, or t squared ends up being 4. I take the square root of both sides, and t ends up being plus or minus 2. Now, we don't normally think about negative time, so the only time I'm interested in is the 2 seconds. So after 2 seconds, this ball is going to hit the ground. So now I know the time I'm interested in. And I have a formula for the speed. So what I'm going to do is say I now know that I want the SDT, or v, I could call this v as well, when t is equal to 2 seconds. So that's just minus 10. Our formula for the SDT is minus 10 times t. So minus 10 times t is 2. So it's going to be minus 20 meters per second. So that is our speed when the ball hits the ground. We find out when the ball hits the ground, and then we use our velocity formula in terms of t to find out what the speed was at that time. Part 4, what's the acceleration? So I know that the acceleration is dv dt, or the second derivative of the distance. And I know the velocity, that's the other name for ds dt, so I have that, that's just minus 10. So if I know v is minus 10 t, then I just get the derivative of that. So dv dt minus 10 on, open up a bracket, this is 10 to the power of 1. So 10 to the 1, 1 minus 1, so I end up with minus 10 on 1. T to the 0, like anything to the 0, is just 1. So I'm left with minus 10 meters per second, or meters per second squared is sometimes how that's written. So that's how we can get the accelerations, just the derivative of the velocity or the speed. Now, separate question. A cannonball is fired. Its distance above the ground is h is equal to 16t minus 4t squared. What is the maximum height of the ball? So, maximum height. Maximum makes me think of dy dx is equal to 0, and d2y dx squared is going to be negative. So that's what I'm going to have to do. I'm going to have to get dh dt, how the height is changing in time, and I'm going to set that equal to 0 to find my turning point, and then I need to show that it's a maximum. So I have my h here, so 16 on 1t to the 1 minus 1 minus 4 on 2t to the 2 minus 1, close my bracket, and I end up with 16 on 1 minus 8t to the 1, and I want to know when that's equal to 0. So I rearrange that equation. When I solve that equation, I just rearranged and got t is equal to 2. I can find the height by subbing that back into my height equation, and I got 16. So 16 meters above the ground is the highest that cannonball gets, and that happens after 2 seconds. Now I should show that that's a maximum by getting the second derivative of d2h dt squared, by getting the second derivative and showing that it is negative. So I'm going to do that now. I get that d2h dt squared, the second derivative is minus 8 for all values of t, so that means that I must have a maximum. So that's how we can problem solve using our rates of change.